All right, ladies and gentlemen. So we're moving on to topic 5 of energy. Okay, it's pages 82 to 89 in your review book, which of course you guys are reading ahead of time and outlining on your own. No, I am not collecting that for homework, but it is definitely a good idea to be reading the chapter before we start it so that way you have an idea as to what's going on. It's obviously not a lot of pages, it's only pages 82 to 98. Okay. Okay. It's a lot of practice problems in there, but that way you have an idea as to what's going on before you get to class. All right, so we need to review a couple of things. First thing we have to do is review energy. Okay. Energy is the ability to do work. Okay. In the morning, especially, a lot of you guys wake up and you're tired and you're like, I just can't handle school right now. Right. And then you sit down and you eat something. Okay. Your ability to do work once you have fed yourself, basically, increases. And the reason is because by eating, you're actually giving yourself some energy or some calories to burn off later. Okay. Because thinking actually does burn calories. Okay. Energy can exist in a variety of different forms. What kind of forms are there, or what did you learn are types of energy?
Electromagnetic energy?
Energy,
Electromagnetic. What else?
heat energy,
Heat energy. What else?
Kinetic.
Kinetic. What else?
Nuclear.
Nuclear.
mechanical,
Mechanical. There's one other one you learned in this class that you can't remember.
Radioactive?
Sort of, yeah. Starts with a P.
potential,
There you go.
Potential
Potential energy. Very good. Okay, so remember, this is review. Okay. So we're gonna start with the electromagnetic energy. We're not gonna go through every single type of energy, but I want to talk about electromagnetic because we've already talked about light being emitted from the stars and what's gonna happen with that light. All right. So electromagnetic energy is going to interact with the environment in 4 different ways. They're reflection, transmission or refraction, scattering, or absorption. And I'll give you guys a second before I explain this so that way you can copy it down. Okay, so reflection is when the energy hits something and bounces right off. Okay, or so you can see it, basically that's all it is. Refraction is a fun one. Okay, refraction, right, is you see my straw here? You see how it's straight? Watch what happens when I put it into the water. It almost looks as if the straw breaks and moves over. You guys see that? Right? It doesn't look like it's a straight line anymore. Right? It's just the way that the light is changed inside of the water. It tricks your eye into thinking that the straw is no longer straight. Okay? It looks like it actually broke when it really didn't. Scattering, the best way to explain scattering is, have you ever heard the expression, you're like cockroaches when the light goes on?
yes,
You know why? What happens when you turn on a light? What happens to cockroaches when you turn on the light?
they run away and they get scared.
Run in every possible direction. That's what scattering is. Okay? Is that it just means there's no rhyme or reason for it. You just go in every possible direction just to get away from that light. Okay, so when you have electromagnetic energy, it can scatter as well, and it can be absorbed. So absorb means to take in. Okay, so those are the 4 different ways that electromagnetic energy will actually interact with the environment. Now, there are properties that will affect how well that energy is going to either be absorbed or radiated. Okay, the 2 properties are the color and the texture. Okay, those are the 2 properties, the color and the texture. Okay, during the summer, right, what colors do you see everybody wearing when it's like 105 degrees outside?
White.
White,
Bright colors.
bright colors, lighter colors. Why?
I still wear black.
What happened?
I still wear black mostly in the summer.
Oh man, I've seen people who are in like full on black outfits
Oh yeah,
summer, and I always feel bad because, I mean, good for you, but I don't know, it's hot.
no, I have friends who don't really care. They're like, oh yeah, it's fashion. Casually wears like all leather and like 100-degree weather.
Oh, leather?
Yeah,
How do you move in that? You've got to be.
I don't know.
That's insane. That's insane. I mean, good for them, but that's insane.
Yeah,
All right,
anything for the fashion.
I guess. As you can see, I don't really care. I can make fun of myself. It's okay. All right. So, they're probably quietly and not saying anything because it's for fashion, but they're probably dying inside because that black color or those dark colors are going to absorb a lot of that heat energy, a lot of that sunlight, which then starts to, heat up your body temperature. Not so much that you're going to die, but the reason you sweat is to actually regulate that body temperature. Okay. Versus if you have white clothes on, then you will actually reflect more of that light or that heat. Okay. Has anybody been I know you guys haven't really been in school for that long, but has anybody been downstairs in the music rooms with those private booths that they have, those soundproof booths?
Yeah.
Right?
Yeah.
What do the insides look like?
There's like foam to absorb the sound.
Exactly. There's foam. What color is that foam about?
Black.
It's a dark color, right? And would you say if you ran your hand up against the wall, I don't say go and like touch the walls, but if you were to, is your hand going to stay straight or is it going to get bumpy?
It's gonna be
Bumpy.
So would you say that's rough or smooth?
Rough.
It's rough. Now, this is very important, okay? Because this concept right here is going to follow you for the rest of this year, if not longer than that, okay? It is soundproof. There's still some sound that comes out, but it's not as much as if you were just sitting in the room, right? The reason for it is because it's a dark color, right? Which we know is going to absorb the energy, right? And you guys just told me it's a rough texture. It kind of looks like egg cartons. The bottom of the egg cartons where all the little eggs sit. If you take it and you like throw it up against the wall, and it's made out of a spongy material. Okay, that's going to absorb the sound more. Now imagine, let's say you're playing your tuba, or let's say a really loud one like a trombone. Okay, you're playing your trombone in the soundproof booth, practicing. Nobody outside hears you. Okay, fine. You take your trombone to the earth science lab and start playing it, right? The earth science lab has a lot of white or light colors, right? The only color in there that they really have is that bright green behind the wall, behind the smartboard, right? Imagine if you're playing that same trombone in the earth science lab how loud that's going to be. Why? Because there's not a lot of textures. It's pretty much metal on metal on metal, right? We have the metal cabinets. We have the metal tables. We have the sleek floors. We have the sleek concrete walls, right? Everything is smooth. Everything is a lighter color, which means that every sound particle that comes out of that trombone is going to be a million times louder. You guys have heard when I've played music in there. The music on the computer is really not that loud. It's just that it bounces all over the place. The sound waves are bouncing all over the place. And this is why. Okay. If it is a dark color and it is rough, it will absorb light. It will absorb sound. It will absorb the heat better than if it is white and smooth, or a lighter color and smooth. It's the same reason why when you guys had snow before Christmas, remember we all wish we had that snow day, but we didn't, right? When you had to go outside and shovel, let's just say you all did, right? When you walked outside and it was sunny out, if you didn't have your sunglasses on, you walked out like this, which didn't help because the sun was coming in every direction, including from below you, because that snow was pure white and super smooth. So all of that light was being reflected up. You guys have all seen it. You try to like walk like this and it's still coming out from underneath you and hitting you in the eyes. Okay? So really, really, really understand that if it's dark and it's rough, it's going to be absorbed. But if it's lighter and smoother, it's going to be reflected. Again, that's going to follow you. Right? So just a little bit of review of the difference between kinetic energy and potential energy. Kinetic energy is the energy of motion. Potential energy is your stored energy. Okay, the Hulk doesn't really like to fight, whereas the Flash likes to run. Okay, the Hulk likes to stay hulky. Okay, whereas the Flash likes to run. Okay, so it's the difference between kinetic and potential. We have transformation. Transformation is a good way of saying going from one type to the other, okay? In the case of the waterfall here, right, you see how the water molecules, or it looks like they're pretty much in a straight line, and then all of a sudden they start to get more misty until it's all pretty much a mist, okay? That's transforming from one type of energy to another, so from potential to kinetic, okay? So it can transform. All right, so let's talk about that heat or that thermal energy. Okay, when you're talking about heat, it is not the same thing as temperature. Okay, how hot or cold something is not telling me how much energy it has. Okay, you think that's important? I have 40 exclamation points here. Okay, so heat is not the same thing as temperature. So we're going to divide and figure out what the difference is between energy and heat. I'm sorry, temperature and heat. Okay, so heat is the total amount of energy, where temperature is the average kinetic energy. Remember, I know it was a long time ago, I think it was like September, October, I said to you, anytime you see the words average kinetic energy, you cross it out and write the word temperature, okay? The reason for it is because they are interchangeable. How fast or slow the molecules are moving, or their average kinetic energy, is going to determine the temperature of that substance, and I'll explain that later. Okay. The units for heat are joules, or capital J, where we know the units for temperature are either in degrees Celsius or Kelvin. Okay. Yes, I could have put degrees Fahrenheit here, but I don't have to include it because we're talking about science. And in science, we really don't use degrees Fahrenheit because pretty much everywhere else in the world, we do not use degrees Fahrenheit.
Miss Gonzalez,
Question.
I'm here.
Who's that?
Stefan.
Oh, okay. Why are you late?
I don't. I honestly, I was waiting till it hit 10:10, and I was clicking on the thing, and it just didn't work.
Okay. Leave
Thank
me
you.
a little note in the chat, please.
Thank you.
Thank you. Okay. And Stefan, make sure you get the notes because we've gone through it a lot already.
Okay.
All right. So heat is the
Thank
energy
you.
value, no problem, where temperature is how hot or cold something is. Okay. So if I was to sum this up, heat is the total number of energy in joules. So you have an energy value. For temperature, it's the average kinetic energy, which we represent in degrees Celsius or Kelvin, and that determines how hot or cold a substance is. Thank you. Good so far. Yes, no, maybe. Good. Okay, well, no news is good news, as I like to say. So, temperature scale. This is on page 13 of your reference table. We've already gone over this, probably towards the beginning of the year, right? You guys had to memorize the temperature water melts and freezes and water boils and condenses at. You guys remember that? Right? And then I showed you that on the Fahrenheit scale, each one of these little tick marks is worth 2, where each one of the lines for Celsius and Kelvin are worth 1. Do you guys remember? Yes, no, maybe?
Yes.
Yeah.
Okay, good. So, for this class, even though I told you to memorize it, okay, it's listed here. All right. So for this class, the freezing point / melting point temperature and the boiling point / condensation point temperature are listed on your reference table. For everything else, every other subject, you need to memorize it because you will not be given these values again. In chem for next year, you will not be given those values. Okay. You also will not be given a temperature scale. So I know I taught you guys that to go from Kelvin to degrees Celsius, it's Kelvin equals degrees Celsius plus 273, right? Remember that formula? It's a very simple formula. You're going to have to know how to convert from one to the other. But since each one of these lines is worth 1 for degrees Celsius and for Kelvin, that means that for every 1 degree I increase in Celsius, I'm increasing by 1 degree in Kelvin. What do I mean by that? The difference between 60 degrees to 70 degrees Celsius is a change in 10 degrees, right? On this side, that's like 333 to 343. That's still 10 degrees. So no matter how many degrees I change in Celsius, I'm also changing the same amount in Kelvin. So kind of goes hand in hand. All right, so we already did this. Okay. Here I have a round bottom flask, okay, with some sort of liquid in it and a thermometer. Now, we're going to pretend that we have super ridiculous powers and can actually see what's happening to the molecules inside of the liquid. That's those red dots that are there, okay? Let's say I put a heat source underneath that round bottom flask. What's going to happen to the molecules?
They're going to be farther apart.
They're going to get further apart. What else?
Are they going to move around faster?
Exactly. They're going to move around faster, right? And as they move around faster, they're more likely to collide, right? They're going to collide with each other. They're going to collide with the outsides of the round bottom flask. They're going to collide with the thermometer. Now, this is an old school thermometer. Most of you guys do not have these at home. However, we do have them in school, and we do have them. Some of your parents will also have them. Not always, but some of your parents will. Okay. They changed the inside of this from silver mercury, like a silver colored mercury, to a red alcohol. Now, this is not consumable. You drink it, you'll probably die. That's not a good idea. Okay, this is pretty much rubbing alcohol with some food coloring in it. so that you can actually see it rising and falling. What happens is that every time, because we've added energy to the molecules so they're moving more, right? So that extra energy, every time there's some sort of a collision, is being transferred. So as the molecules hit the thermometer, it transfers that extra energy into that rubbing alcohol, making it go up. See? Okay, so that the more that the molecules, oh goody, the more that the molecules are moving, the more collisions you will see, okay, and the more that the temperature will increase. All right, so that's how you get an increase in temperature, and that's why there's a problem with those thermal scanners, because it's reading your surface temperature. It's not actually reading your body temperature. These are the best types of thermometers, and the best way to take your temperature is actually through your butt. The best way to get your internal temperature. It's not pleasant. You probably had it when you were a baby. You've probably seen your animals, if you have them, when they go to the doctor, they don't get their thermal scans. They get a thermometer up their butt. It's not pleasant to watch, and the poor animals freak out, and it's just not fun. Okay. But that's how basically everything works. Okay, so here we have two different containers that are open, so there's no cover on them, okay? And they have molecules inside of them, all right? They should have the same amount of molecules so that you understand it a little bit better, but if we're looking at this, okay, colder molecules are going to be closer together. Think of it like this way. If you guys are all outside with a group of friends during non-COVID, and you're all hanging out, right? And you're waiting for the bus. What's going to happen? If you're really cold enough, you're all going to stand closer together. You're going to huddle for warmth, okay? By huddling for warmth or making those molecules move closer together, what happens to their density?
It increases.
Right. So if their density increases because they're closer together, right, they're going to fall to the bottom of the container. Okay, or if we're talking about air, cold air is going to sink for that reason. Okay, hot air is going to be the opposite. They're moving around more, right? You've increased the temperature, which means that you've increased their average kinetic energy. When you increase their average kinetic energy, the molecules move further away from each other. Okay, which also means that they're going to be less dense, and less dense things rise up. Okay, so that's why hot air rises and cold air sinks, right? So the more heat that we add, you see how the cold air molecules are falling. Here, I'll go back to the beginning. You see how the cold air molecules, as they lose their energy, start to sink down, where the hot air molecules are rising up. That's why during the summer, you don't want to be in your attic, because that's where all the hot air will be, unless you have central air. That's a whole different story, or a house fan like I did. And the coldest place you want to be, most basements don't have an air conditioning unit for that reason, because they don't need it. If your basement is below ground, you don't need it, because you're at the lowest point, and all that cold air that you have circulating upstairs is actually sinking down. Okay, so
What was that big sound?
it's on my PowerPoint. Okay, it's like a typewriter. I'll explain to you what a typewriter is later. Okay. Go. I got a class. You can't see them because they're behind the PowerPoint. Go. I gotta teach. Okay. All right. So specific heat. All right. See, look, all the kids are here. See them? They're all there. All right. So specific heat. Now, this is a chem concept that you are going to begin to learn in earth science, right? It's not as complicated as it seems to be at first, okay? For this class, you will not be required to do the actual math before, with it. I'm going to show you how to do it just to give you my point, basically. Okay. Like make my point. All right. So what specific heat is that first of all, if you look at page 1 of your reference table, okay, you will see a chart in the top right-hand corner. All right. Did everybody look at their reference table? Right. There it is. Yay. Okay. You'll notice that each individual substance here has a different specific heat value. There's a reason for that. Okay. So what is specific heat? Specific heat is the amount of energy that is necessary to raise the temperature of a 1 gram substance by 1 degree. Now remember, I said later. We said that later. Stop.
I can do this
Okay.
later.
You get in trouble.
Mom, if you're
Go.
done, I can do
Yes.
this.
Go. So, okay. And we use this formula Q equals MC delta T. I'm going to explain all of this. Well, you guys are doing that. Let me know when you guys are ready. Is anybody still copying?
No.
Okay. So, all right. Here's the formula that's called the specific heat formula. Okay. It's Q equals MC delta T, where Q is going to be your heat value, which we know our units is joules. M is going to be your mass in grams. Okay. Capital C stands for your specific heat capacity, that you are only responsible for knowing the ones or recognizing that they are on page 1 of your reference table. Okay. And that's in joules per grams degrees Celsius. Okay. Upstairs. Take that upstairs. 1. Go. Okay. And delta T. Do you remember when we did, we were talking about the slope formula, right? It's the change in Y over the change in X. And we represent the word change by a triangle or a delta symbol. Okay. Anytime that you see delta, it's going to represent change, or it's going to be the final value minus the initial value. Okay, that's why it's Y2 minus Y1, right? You guys remember this from math? No? Yes? Maybe?
Yeah.
Okay, good. At least somebody knows. All right. So, you can have a negative change, right? If you started at 100, or if you started at 0 and you went to 100, your change is going to be a negative number. That's okay. All that means is that your heat is going to be released instead of absorbed. That's all that negative number means. Okay? So, going back, you guys okay? Can I go change the screen real quick?
Yes.
Thank you. Okay, so going back to our reference table on page 1. Okay, this specific heat values that are here. are listed from liquid water at 4.18 joules per grams degree Celsius all the way down to lead at 0.13 joules per grams degree Celsius. Okay? Big difference in numbers. Very large difference, right? What this tells me is that in order to heat up water, we need to put in 4.18 joules of heat versus lead that we have to put in a very small number. So lead is going to heat up faster than water. That's what this means. Okay? Hopefully I can go to school today and grab the material I need to show you guys tomorrow how this actually works, but we'll see. So I wanted to prove to you using numbers. Now you are not responsible to do the actual numbers, okay, and plugging it in. All right, but I want to show you, right? If we have a 10-gram sample of water and a 10-gram sample of lead, same size sample, just two different materials. If we want to change the temperature of both samples by 50 degrees Celsius, the difference in heat that needs to be absorbed is a lot, okay? Because it's based on your specific heat value, okay? The amount of heat that you need for water is 2,090 joules. For lead, it's only 65. That tells me that lead is going to reach that 50-degree difference much faster than water if everything else is the same. So in other words, as we're going through, if you have 4.18 divided by 0.13, okay? So as you're heating this up, lead is going to change temperature values 32 times before water changes by 1 degree. How did I get that? I just took the specific heat values and divided them. Okay, so you're going to increase the temperature on the lead sample 32 degrees before the water sample gets increased by 1 degree. Questions? I guys have no questions because this is a kind of hard concept to understand without seeing it. Okay. This is why when you go to the beach, right, during the summer, your feet are burning as you run to get to a good spot by the water. But when you put your feet in the water, it is freezing because the ability to heat up or cool down sand is much greater than the ability to heat up or cool down water. Does that make sense, guys? Kind of, sort of, maybe. Victoria, you good?
Yeah, sorry.
It's okay. Trying to see. Oh no, it's in my PowerPoint. Okay, so we're gonna watch this little specific heat video, and it might explain it a little. Oh, maybe not. It did not want to copy. Hold on one sec. Sorry about that. If this makes it a little bit easier. Commercial. Commercials.
Hi everyone, welcome to the Earth Science Regions Review podcast series created by Hamilton Middle School Earth Science Department. Today we're going to be talking about a phenomenon called specific heat.
Actually, you know what, guys? The bell is about to ring, so I'm going to end it there. Does anybody have any questions before I let you go?
We're not going to need to know how to do that this year, right?
You're not going to need to know how to do the math portion of it, but you are going to have to understand that because water has a higher specific heat, it's going to take longer to heat up and cool down compared to the other things that are listed there.
Okay.
So
Is that due to like the density? Like, cause
not really, because lead is much more dense than water.
yeah, that wouldn't make sense.
Yeah.
So what is it like? Why does water take longer to heat up than like lead?
Because of that specific heat capacity, which we will get more into tomorrow, because guys, the bell has rung. Okay. So if you guys would like to go, you can. And I will see
Bye.
you.
Have a good day.
Bye, guys.
Have a good
I
day.
have a good day.